talk on scattering and spinning black holes. I don't think we were here on the first day.
No.
When we had the introduction round, so we want to tell people maybe very briefly what your general decision is.
Right. Okay. Guess that will become apparent. But yes, so I'm a postdoc at UCLA and jointly in Potsdam, in Alessandro's Bonanos group and Seaburn group at UCLA. And yeah, my research interest, so since my PhD, I've been working on gravitational waves on the modeling side. So let's say, started working in the post-Newtonian approximation to general relativity for solving the two-body problem, in particular with tidal effects. Was my beginning work, and then did a little bit of work in self-force during my PhD. If you don't know what that is, hold on just a minute. And since moving to Potsdam, I've been involved again with more post-Newtonian approximation and post-Minkowskian approximation, various perturbative approaches to the two-body problem. That's the theme for the whole talk. And yeah, so thinking about analytical, semi-analytical ways to solve binary black hole or binary neutron star problem for applications in gravitational waves. It's my general area. However, what does that have to do with scattering amplitudes? So more recently, I guess you've heard, also I missed Mao's talk on Tuesday, but I'm guessing you heard a lot about relatively recent developments, especially since the discovery of the first gravitational waves in 2015. A lot of people, in particular particle physicists, got excited about modeling gravitational wave sources, and it has become apparent that a lot of technologies that were developed for analyzing scattering amplitudes in particle physics and quantum field theories, some of those same computational techniques can be very powerfully, usefully applied to the classical gravitational two-body problem. And so I'll tell you a little bit about some of those developments and more particularly things I've been involved with. But okay, so moving to my first slide. Again, we want to think about the binary black hole problem emitting gravitational waves as seen by detectors such as LIGO, Virgo-Cagra, and coming soon, NISA in space. And so I'm showing here two black holes with masses M1 and M2 separated by a characteristic distance r, moving at speeds roughly v. And in particular, a lot of my talk and my work focuses on the effects of the spin of the black holes. So you may be aware that in a certain sense, inside a spinning black hole, instead of a point singularity, there's like a ring singularity in a certain sense. So that's what's pictured here in green. And the radius, how does it work? Oh, it's working. Okay. So here are these ring singularities with radius a. If S is the spin or intrinsic angular momentum in full units, divide that by the mass of the black hole times speed of light, that gives you a length a, which is in a very specific sense the radius of the ring singularity, or the rescaled spin a. And well, okay, let me first come down here. So regimes in which we can perturbatively attack this two-body problem, the most useful for LIGO, let's say, is the post-Newtonian approximation, where we assume, firstly, that the characteristic gravitational potential, so gm over r, divided by the speed of light, we assume that's small. So that's a weak field assumption. Now, if you have a bound binary, essentially the Virgo theorem tells you that's of the same order, like gm over r, the potential is of the same order as v squared. In particular, for a circular orbit, one is minus a half the other. So for a near circular orbit, these two small parameters are basically the same. And we assume that they're small, that's the post-Newtonian approximation. Weak field, slow motion.
And spins are non-parallel, so it's the matter.
It matters a lot. So it's certainly simpler when they're parallel and orthogonal to the plane of motion. Because then, in a certain sense, the degrees of freedom are the same as without spins. The spins only appear as a parameter, the motion stays in a plane. But if the spins are not, then the orbital plane precesses, the spins precess, it's much more complicated.
So which is the variable which is relevant in this approximation?
I'm sorry?
Which is the variable, it's not just A that's relevant.
Ah, okay. So it's good.
You stop to share screen.
Yeah, I can't see the slides now, sorry.
Zoom landing is completed.
This meeting is being recorded. Got it.
So you have to share again.
Share again. Okay.
It's good, thanks.
So, all right, about the spins here. So this ring radius A, if it's actually a black hole, this A is bounded by the Schwarzschild weakness, GM over C squared. So that's why, let's assume that it's almost maximally spinning. So that's why this is of the same order as this. So these are all basically the same small parameter. Did I answer?
Yeah, so you said they're correlated, so one is small, the other is.
Right, exactly. If it's actually a black hole instead of a naked singularity, so I'm pointing out here, if it's actually a black hole with a horizon, A has to be less than GM over C squared, but it could be bigger. Of course, then it's not a black hole, it's a naked singularity. And so moving down to the next line, so that's the most useful, most directly applicable approximation that has a very long history, and LIGO data analysis would not be possible without lots of work in the post-Newtonian expansion. So an alternative is, okay, let's assume weak fields, moving down to the next line, but let's not assume small speeds. Okay, but I just said, if it's a bound system, V squared is the same as GM over R. Okay, but just imagine, what if we wanted to access this regime? Well, we could have, say, a scatter. So an unbound orbit could access the regime where the fields are still weak, but the velocities are arbitrary. And strangely here, I'm saying, okay, what if we also treated this A over R as not necessarily small? So that's a strange approximation. And as I said, to access that regime, you'd have to leave black holes and go to naked singularities. Why would you want to do that? Well, let me leave that question for later, but why would you even want to do this work with arbitrary speeds, but still weak fields? So this is the so-called Minkowski approximation. Well, it turns out, so in the next slides, I'll try to motivate why that's interesting. Maybe Mao also talked a bit about that, but
Sorry, you lost again the.
I think every time you speak,
okay,
it's going to require you to reach your table, stretch this 3 times.
yes, probably. Where do I find that display? Battery. Sorry.
Go right. Go right.
Ah, yes.
Go there.
Never.
And then you need to reach there.
And reach
again. When it's being used, that's great.
Okay.
Good.
So for now, let me just say that thinking about scattering can teach you a lot about bound orbits. And in some ways, scattering is a much simpler problem. if for nothing else, that you start at infinity where things are simple, space-time is basically flat, and you end again at infinity with simple incoming and outgoing states, and things are a lot cleaner, I'd say, than Gauss movements. And furthermore, will come this connection to scattering amplitudes. And technologies from quantum field theories for dealing with scattering amplitudes that allow one to calculate things to higher orders in these expansions more easily and gain insights into structures in the problem, as well as the fact that learning about scattering also teaches you about boundless in certain ways. Okay, one more approximation scheme. Can we get away with assuming neither weak fields nor small speeds? Yes, if we assume a small mass ratio. So say, like in this picture at the bottom here, one of the black holes is much smaller than this. So now our perturbation scheme will be, so here, we started basically our 0th order approximation was Newtonian gravity. Here, our 0th order approximation is flat spacetime. And here it's going to be an exact strong field black hole, so Schwarzschild or for a non-spinning or a Kerr solution for a spinning black hole. But we imagine the small body now as a perturbation on top of that exact strong field black hole and do so-called black hole perturbation theory. So solve for the gravitational field created by the small guy as a perturbation to this curved diagram. And so at 0th order in that approximation, let's forget the spins. So at 0th order, this little guy would follow a GD of the Schwarzschild spacetime. So perturbing away from that, it has its own field, and effectively looking at it as something happening in this background, it has a self field which exerts a self force, which is where this name comes from. It's a strange name, could be better called the extreme mass ratio situation. Here I'm calling it post-probe. Probe is another word for a test body. It's more popular with particle physicists. So the self force makes it deviate from geodesic motion and spiral into the big black hole, which it wouldn't. So geodesics in a bound orbit would just stay that way forever. But you turn on the effect of this self field and it starts inspiraling. So that's a very hard approximation scheme to, solving wave equations on a Schwarzschild or a Kerr background. But in the past 20, 25 years, people have made a lot of progress in this area. And the point here is that these are all three very complementary approximation schemes with overlapping regimes of validity. And recent developments related to amplitudes have revealed powerful relationships between the different schemes. And that'll be the first point that I want to get across. Forgetting the spins, but one more thing before we get to that. So about that, when you go in this extreme mass ratio limit. Oh, okay. So first, the problem we really want to solve is the real binary black hole. They both have finite masses and spins, and then skipping the middle line for now. Like if we took a physical limit where the little guy gets very small, it's just going to become a point, and the 0th order approximation will follow geodesics in the Kerr space. But I'd like you also to consider, we'll come back to this stranger limit where I take the mass of one of them to be negligible compared to the other, but I keep it to have a finite ring radius. So that again goes past, so now it's a naked singularity in a certain sense. But it's not, and its mass is negligible, its field is negligible, but its structure is not negligible. So it has, say, multiple moments, or say all of its mass rescaled multiple moments. I keep finite in this limit. And I'm claiming that's a very powerful limit to consider, because my first point here that I want to get across is that results for arbitrary mass ratios in post-Newtonian or post-Gaussian approximations can come and to a surprising extent from this extreme mass ratio or test body or probe limit and its perturbations, the self force. So that's what I'll describe now. First, forgetting spins and then coming back to spin.
If the only one of them is spinning, does the other spin have any effect?
If only one of them is spinning, does that spin have an effect? Yes. So the orbital plane, unless, so say the big guy is spinning and the other guy is orbiting, if that orbit is perpendicular to the spin, it stays in the plane, otherwise the spin and the orbit persist.
But that would be self-incoming anyway.
It still affects the Hamiltonian dynamics.
Absolutely.
It's not an equality.
So you mean if it's aligned?
Yeah.
Yes, it certainly has an effect, but the orbit stays in a plane.
Just
Yes.
could we think about this test black hole limit and think about maybe beyond just giving it a high spin? I mean, thinking about a Newtonian star, its mass might be small, but its tidal moments and other other structure on top of being point particle could be enormously significant. So this is kind of the same philosophy.
Absolutely, yes. And it could be like a satellite that's not spherically symmetric, and its size, or if it's spinning also.
Yeah.
Even though its field is negligible, you can't just model it as a point. Its structure is important. Oh, absolutely. It's much less weird to think about that than the naked singularity black hole thing. But I still think that's a very useful thing to think about, even though it's not good. Okay, so forgetting spins for a moment. Here I'm looking at so in the post-Newtonian approximation, there's a task. We want to solve for the orbit of a binary system, and that can be made in the post-Newtonian approximation. Looks like the Newtonian problem. So I draw a line here, and I'm going to call this 0 PN, or the Newtonian approximation. I hope you will recognize the Hamiltonian for the Kepler problem, the Newtonian two-body problem, with the momentum squared and the potential. And so this is in terms of 3-vector position R and momentum P. And then you see next here, so-called first post-Newtonian approximation are corrections to that in 1 power of the small parameter that was on the first slide. So these all have a 1/c². We can formally think of the post-Newtonian limit as c goes to infinity. 1/c goes to. And these were first computed in 1917 by Lorentz and Droz, and people forgot about that. They thought for a long time that actually it was first done in 1934 by Einstein, Hinfeld, and Hoffman. But in any case, a long time ago, this first Newtonian correction was worked out, and going to the next end. So how, I'm not going to talk about, but essentially it's solving Einstein's equations in a perturbative scheme in 1/c², starting from Newtonian gravity, realizing, of course, firstly, most importantly, that as c goes to infinity, gr becomes Newtonian gravity. Then the next order, 2pn, 1/c⁴ was worked out in the 90s, is that right? By many people, including, for example, T-1 and Grant Schaefer. So that was a long gap. The next one, I'm not drawing, but I'll just mention. Third post-Newtonian 1/c⁴, I think, was the next decade. And rough 4pn was, I would say, roughly worked out in the decade after that, and with it in this decade, working on 5pn. Or I'm not sure. It's not, is it settled? 5pn. Almost. Very close. That's a very good question and point I want to make. So it looks like, I don't know if it's easy to see, but yeah, it looks like a Newtonian order, we have essentially no dependence on the mass ratio. So the symmetric mass ratio, is the reduced mass, which you recognize from the Kepler problem, like in the Keplerian two-body problem for masses M1 and M2 is equivalent to the motion of a test body of irrelevant mass mu in the field of the total mass big M. Okay. So that's in a sense why the 0 PN doesn't depend on the mass ratio. Whereas it looks like at 1 PN, it's linear in mass ratio. At 2 PN, it gets up to quadratic in mass ratio. I don't have a good answer for why, but that's how it turns out. Absolutely. And so that's the self-force approximation. And we can solve that to all orders in 1 over c squared or in G. That's GD6 and Schwarzschild. So it looks like we have this kind of mass dependence. And this is the classic way that these kinds of results are used, packaged in a Hamiltonian function like this. For example, these EOB models, which we've heard about and used this morning a bit. They literally take exactly such a Hamiltonian and get Hamilton's equations from it and numerically solve Hamilton's equations. So this is the way these kind of like final results ready for use were packaged in exactly this kind of form. But you have to keep in mind, for example, this is a gauge. This is not gauge invariant. This is subject to, let's say, general coordinate transformations in GR, or here in the Hamiltonian canonical transformations. And so I could do changes of variables that are going to mix up all these coefficients. And furthermore, I'm claiming like this hides a lot of structure, in particular, that comes out when you think instead about this so-called gauge and this scattering angle function. So take that Hamiltonian, or any such Hamiltonian to any order, and basically solve the equations of motion for a scattering situation, and find the angle chi by which both bodies are scattered in the center of mass frame as a function of the impact parameter b, and let's say the relative velocity at infinity, which defines this gamma Lorentz factor. Okay. So first claim is that's a gauge invariant function. All of the gauge dependence in that Hamiltonian is gone if we compute this function from it. Secondly, an important claim is we didn't actually lose any information. All of the information that we lost is gauge. To verify these claims, you would just, one way to see that that's true is to count all of the coefficients in the Hamiltonian, count all of the coefficients in the scattering angle function, and count all of the coefficients in the most general canonical transformation that you can do to the Hamiltonian. It adds up that you didn't lose anything. So given just this scattering angle function, I can reconstruct the Hamiltonian modulo gauge. And that same Hamiltonian governs both scattering and bound orbits. So yeah, please.
So to help me out here, so what I can see that working. So I'm thinking, so in the following case, when I add this, there are scenarios where I have resonance, and then they introduce a very interesting phenomenon. What does that map into the scattering? Like that, like just got no intuition.
Well, resonances.
That means the scattering angle diverge.
The scattering angle function does have poles that do correspond, like for example, to capture. Like a best example is the Schwarzschild GD6 scattering angle function. There's a critical at a given velocity. There's a critical impact parameter where you're going to fall into that horizon. So that appears as yes, a pole of the scattering angle function. Okay, that's not exactly a resonance, but okay. Yes, Aaron.
Yeah, I guess when it comes to the scattering angle, I can see that this thing is now a function of two things which themselves might be gauge invariant if I think about measuring them at asymptotic infinity on
Right.
some flat space. But if we're going to map this now to a bound orbit, we lose, I would think we lose the ability to measure something at asymptotic infinity where we have that kind of control. So what are the gauge invariant things that
Questions. So I would say instead of this gamma factor, which actually becomes no, it just goes less than 1, but V becomes imaginary for bound orbit. Anyway, they should be replaced by the energy and the orbital angular momentum, or the angular momentum, total angular momentum. So, I mean, you can see here a direct map, at least for scattering between gamma and the energy. But the energy, total energy of the system, like ADM mass, is still a good variable for bound orbits. So is the angular momentum.
because we can measure those two.
And there is, so, you know, this relation between the energy and this gamma factor, that's just basic special relativity. There's also some basic special relativity that will tell you what is it, I think, 1, 2, over E gamma E B is the special relativistic expression for the total angular momentum for the unbound part.
Sorry, I'm not sure, but can you tell me what?
So very concretely here, I was mentioning in that Hamiltonian, we could do canonical transformations. Those, yeah, R and P. So R and P go to any function of R and P that leaves the Poisson brackets in their canonical form. That does include and is more general than general coordinate transformations in this space-time. Any other questions? Going very slow. That's okay. All right. So besides these cool things about this function being gauge invariant and having all of the information, there's some remarkable structure that's revealed when you say compute from that Hamiltonian, for example, or just say solve the actual post-Minkowskian. All right. I need to go back and say, so we're looking here at the post-Newtonian approximation are the columns I was making, but you can see here, sorry, these rows are the reorganization into the post-Minkowskian approximation. So basically thinking formally, our small parameter in the post-Minkowskian approximation is Newton's constant G, the couple. So there's that reorganization. And now I'm claiming, so actually in 1985, a guy called Westphal directly solved Einstein's equations in the post-Minkowskian approximation to get this scattering angle function through order G squared, second post-Minkowskian order. And we see quite a remarkable structure here in that apart from this overall factor of the energy over the mass, which has some kinematic origin, there is no dependence on the mass ratio in this function. In terms of these variables, that's very important. In terms of impact parameter and the Lorentz factors, I would call those geometric variables. So in a sense, here we lose no information by going to the test body number. I could recover this complete result for arbitrary masses up through G squared, and notice that's going to get everything here except for that 1 3 p.m. term at 2 p.m. just from this very simple expression, which is gauge invariant and displays this remarkable dependence on the mass ratio.
Again,
Yeah.
how do you see it's gauge invariant?
Okay, right. Okay, so the first very concretely, I consider the most general canonical transformation of that Hamiltonian. And like perturbatively, you can just enumerate all the possible terms. And then I do that, and then I compute, and I see it doesn't change.
In field theory, normally it's gauge invariant, and you're in terms of gauge invariant quantities. You can't write this in terms of gauge invariant quantities, but it's say, okay, it's gauge invariant.
Well, I would say that the energy and the angular momentum are gauge invariant quantities. And at infinity, they have these simple relations to this gamma factor and the impact parameter.
Okay, so then why do we have to check it if you don't make sure that it's
I think the non-trivial part of the statement is that it encodes all of the dynamics of the movement.
No,
Now that it's gauge invariant.
the physical I'm not asking, but I'm just asking about the statement, it's gauge invariant.
Yeah.
So can you just say it's gauge invariant without checking it, or do you have to actually check the gauge invariant?
You probably, I agree. It makes sense that it is gauge invariant, but you can also check,
Okay.
and it is. So no dependence on the mass ratio at first and second orders, and amazingly, and this wasn't known until I was going to give a couple of references on the board. So first of all, I was going to say this resurgence of interest in the post-Minkowskian approximation, I think, can pretty fairly be traced to a paper by Tibor Moore in 2016, where even though I'm not going to explain this, he pointed out that EOB is exact. Ask me for details. He had another paper in 2018 where he was looking at, TPM and asking, very specifically. Oh, thank you. Yes, that is specific. That's okay. He very specifically said, hey, particle physicists, hey, scattering amplitudes people, you should be able to compute the order G cubed scattering angle with your fancy scattering amplitudes methods. And so they did that. Actually, do you remember, was this 18 or 17? I think this was 17.
I can look it up if you want the archive number.
It's just a year difference, plus or minus 1. So in January 2019, that happened. And that was really the kickoff of, is that right? 2019, yes. Yes, January 2019. They computed that contribution to the scattering angle using, so it's going to say amplitudes or C mouse talk.
So this is where you cover what's focused.
Yeah, there was actually a paper, a very important paper that came in 2018 by
17, yeah, 17 the applied, 18 the theoretical.
right. There are very important, two very important papers by Rothstein, Rothstein Solon. Yes, they reproduced the 2PM from amplitudes. There was also a paper by Björn Bohr et al. That essentially did the same, came shortly thereafter. And then in January 2019, this G cubed level. And only after that was it noticed that remarkably, written in terms of the right variables, that's only linear in the mass ratio. And I better speed up a lot. This was, yes.
Sorry to keep you from speeding.
That's okay.
So is the fact that there's a much more non-trivial mu dependence up to 2 p.m. in the Hamiltonian you've written down than in the scattering function that's supposed to generate the Hamiltonian? Is that just because that Hamiltonian isn't written in the best coordinates? Is that the idea?
Yeah, it's I mean, I want to say that on the one hand, like it's not a good quantity because it's not gauge invariant.
But we
But
know how to
that's
generate
not-
dynamics from it.
Sorry?
But we know how to generate dynamics from it.
Right, absolutely. Yes. It's just that, yeah, this structure is obscured. And it's not that there exists a gauge where this mass ratio dependence becomes true. It's just that, yeah, looking at this clean situation of coming from infinity, going back to infinity, with gauge invariant things, working with the right variables, that's important, geometric variables.
Just
Bring down the introduction.
quickly. So in the 2017 paper by Dan, I read literally from the abstract, who urged amplitude experts to use their novel techniques to compute the two-loop scattering amplitudes of scalar masses, which is exactly what Bert and Tal delivered 1 year and a half later.
Exactly. Yeah, so literally in the abstract, he's asking.
Yes, and so he did.
And they did it. Since then, by the way, they've gone on and did G the fourth, working on G the fifth, although things get complicated as for what part we're talking about. So everything here, of course, I've been talking about is the conservative dynamics. In fact, up through this level in the post-Newtonian approximation, that's all there is. The radiative or dissipative stuff starts at order 1/c to the fifth, or so-called 2.5 pm order, which is another story. But yes, continuing to focus on the conservative dynamics. This was an argument that was given by De Moor in Sorry, yeah. So on this slide, these are the first 4 digits of the archive numbers. So a paper by Thibault in December of this January year. He gave an argument which didn't have anything to do with amplitudes that explained this mass ratio dependence. And instead of going through all of that, I would say it's essentially just thinking about the structure of post-Minkowski expansion, Poincare symmetry, dimensional analysis. You arrive at this fact that so from, I'm going to call this 0th order self-force. So that's the test body limit, the probe limit. From that, you can get 1 and 2 post-Minkowski. And if you re-expand in 1/c, that means you can get Newtonian and first post-Newtonian. And from first order self-force, you can get 3rd and 4th post-Minkowskian, or 2nd and 3rd post-Newtonian, which was an amazing revelation in 2019, especially after all the years of the effort that went into doing these post-Newtonian calculations. And so 3P, for example, the 3rd post-Newtonian, which you could get from, say, a first order self-force calculation, that had already been done. So you couldn't get anything new from this realization. By the way, this pattern continues in the obvious. However, with spins, so everything I've said so far, all this Hamiltonian stuff is without spins. With spins, and say just even starting just at linear order in the spins of the objects. So the so-called spin orbit effects. There was a small window. Let me come back. So in 2019, when this realization about the mass ratio dependence came, so here, if you will, on the top line is the non-spinning part with post-Minkowskian corresponding post-Newtonian orders, if you re-expand one over C. The second line is linear in spin or spin orbit effect. And at that time, the state of the art there was there. And so if you can extend De Moor's argument to include spins, like if you can extend this to include spins, you could then get this 4th or 3rd next to leading spin orbit contribution at 4.5 pm, in principle, from a first order self-force calculation. So that was done by my collaborators and I in this paper in Don't have any data. Yes, question.
I think I know the answer, but just to be sure, you can't run this the other way, right? I can't take PN.
Because in, so the self-force results in general are, to all post-Newtonian orders in principle. Of course, you need these analytic solutions like using MST, etc. But yeah, no, you could only get the post-Newtonian expansion of the self-force results if you try to go there. But it's simple, you just take the mass ratio. Okay. And in the interest of time,
And there's no talk afterwards. So
okay,
I can speak for others, of course. I think most people would be interested to hear the whole story.
okay, well. So I was just mentioning our work to use this remarkable dependence on the mass ratio, and so in the end, none of that work I was just mentioning actually used amplitudes, but it never would have happened if this hadn't happened. To notice that mass ratio dependence, and then in hindsight come up with classical arguments for why that is. But so you can see in this table, let me see, where's the current state of the art is here, maybe here, depending on soon to be here, and it's still right here. Very recently, having again actually nothing to do with amplitudes. No. Sorry, yeah, no. Well, it was first done without amplitudes using traditional post-Newtonian or at least EFT methods. They got what happened? Do I need to reshare?
Yes.
Yeah, we lost the broadcasting.
I don't know why it's.
So it might be YouTube.
And then everything's good now?
Yeah, please go.
The current state of the art is somewhere around here. I would say definitely not including that one. Including these guys. However, these guys, for example, so this is going to high orders in spin, but at low relative post-Newtonian or post-Minkowskian orders. So the two that I just circled. These guys, I would say, were for the first time computed using amplitudes methods. Now, notice in principle, so these are just the next to leading ones. In principle, you should be able to determine these from the test body length. If this thing holds true, even with spins and two arbitrary orders in spin, which it seems to. I think, and you can make an argument for why it should. These guys were not, well, so there becomes a question at higher orders in spin, which correspond to higher orders in multipole expansion of the black holes. So I should mention here, important fact. So a black hole, when it's spinning, same for a neutron star. Spinning, it's no longer spherical, it becomes oblate. In fact, it has a quadrupole. So black hole or neutron stars have a quadrupole moment, Q, proportional to the spin squared. And in general, there's a proportionality constant here. Actually, let me write this rescales. And then I can get all the units right. So you'll see it's quadrupole because it's mass times the length squared. In general, there's a coefficient here, which for neutron stars is of the order of 4, 5, 6, 7. There's a special value for black holes. So these kind of effects, this quadrupole effect in higher orders of the multipole expansion, are important at these higher orders of spin. And so a black hole has an infinite tower of higher multiple moments, a quadrupole, octupole, etc., all determined by its spin. These get involved at these higher levels in the spin expansion. And so as I was saying, these next to leading order, spin cubed and spin to the fourth, were actually derived for the first time from amplitudes. And even though, which I hope to say a little bit about, but again, I said in principle, you should be able to compute them from just the test body limit. But it should be this weird test body limit that I was talking about. This taking the mass to zero at fixed ring radius. So how do you describe that object? And I had already mentioned here the math is in Vector-Dixon equations. So again, for a moment, leaving aside amplitudes, just thinking about classical calculations. What are those? Well, well, that's a big equation, but I mean, for a moment, just don't look at that, look at the board. And how do you describe even a point particle in principle, even before solving Einstein's equations? And you would say, let's say there's an action for the whole system, which is the Einstein-Hilbert action, integral of the Ricci scalar, plus, how do I describe a point particle? Well, I say it has a world line. Essentially, I think that can be Einstein. It has a world line in space-time, and its action is the proper time along the world line. So this is an action which in principle encodes everything there is to know about the motion of a structureless point particle. Okay. Vary this action, what you get is the particle should follow a geodesic of the space-time. You also get a source for Einstein's equations, which looks like a delta function stress energy tensor along the world line. Now, going on to solve those equations is the whole problem in the expansion of Newtonian, post-Minkowskian, or self-force. But in principle, this defines the dynamics completely. Okay, so what if I want this guy to be spinning and to have higher multiple moments? So that's what's up here. I'm writing down an action that where the degrees of freedom are, again, a world line and its tangent, and now a momentum, which is conjugate to it, which I also independently vary, and a spin tensor, relativistic spin tensor, a tetrad, a frame field along the world line, and I don't have time to get into these technical details. Let me just say this is some Lagrange multiplier term that fixes a choice of the world line for experts. It's called the spin sublimiting condition. But then essentially some function that encodes the coupling of the object's higher multiple moments to space-time curvature. The spin orbit coupling to gravity is essentially encoded in this term. But the couplings to all the higher multiple moments are down here. So for example, this encodes the spin-induced quadrupole that we were just talking about here. So it's the Riemann tensor, which is space-time curvature, contracted into two copies of, here this is the spin vector, defined in this way, the Pauli-Urbanski spin vector, defined from the spin tensor. But you can see anyway, it's spin squared times curvature. That encodes exactly this coupling that we're talking about. The next, and here the coefficients are all fixed so that this describes specifically a black hole. Sigma is the spin vector, which is defined from the spin tensor here. So this is like the special relativistic angular momentum antisymmetric tensor, and we take essentially its dual and contract that with the four velocity that gives you a spin vector, so-called Pauli-Urbanski spin vector. And this has an extra power of spin and a derivative on the Riemann tensor, and this is telling you about the spin-induced octopole moment of the black hole, which is proportional to spin. And so this is in principle an infinite expansion. But in the spirit of effective field theory, we should be writing down all operators that we possibly can with these ingredients in our action. With only degrees of freedom are the world line, its conjugate momentum, and the spin tetrad that's rotating around and its conjugate momentum, which is the spin tensor. But going through this exercise, writing down all possible couplings, if you restrict yourself to linear order in the curvature, you get this infinite series, which you can imagine, which is keeping on adding a spin vector and a derivative. And we know what those coefficients should be basically by matching to the Kerr solution at the linearized level. But at this level in particular, spin to the fourth, where we've got two derivatives of Riemann tensor, becomes most particularly important to start considering Riemann squares, so curvature squared terms, times spin to the fourth.
So the third term on the first line.
Third term on the first line
Second zero.
is,
P is proportional to U.
sorry, with the one I just underlined?
Yeah.
Right, so this condition is something we want to enforce. And so beta is a Lagrange multiplier that's enforcing it. Yeah. It's setting to zero the mass dipole moment.
It's just like an SC2.
Essentially, yes. And in a way, it actually can fix a choice of world line, a representative center of mass. Yeah, we're saying the mass dipole should be zero in the frame of the moment.
People don't grasp the importance.
People do use.
Well, people do.
Effective field theory, that's the.
Okay, so.
But you mean like these Grassmann?
It's just an alternative way of defining S, but I guess the answer is it's equivalent.
That's right. And people do use that,
You mean the Grassmann variable?
the Grassmann.
Yeah, the problem is that when you go to a higher order interaction with Grassmann,
Yes.
as we found out in the master physics
Who's master thesis?
of Gilbert's.
Two joints to the right of it, years ago.
Yes. Right. So I was saying, like the point I want to get across here is by some simple matching at the linearized level between the Kerr solution and this kind of effective action, you can be pretty confident about all of the, well, you can be very confident about all the terms that are going to be linear in the Riemann tensor and its derivatives. But you know nothing about possible curvature squared couplings, and those become important for leading orders in the post-Minkowskian expansion, precisely here at fourth order in spin, because that's when I can start trading two derivatives of the Riemann tensor for, say, Riemann tensor squared. So now, and remember, this was all in the context of, if I could just solve this in the test body limit, I would have first and second post-Minkowskian orders for arbitrary masses. But I can't even do that because I don't even know what the equations of motion are supposed to be for this test black hole once I get up to this higher order instead. And including all the relative terms. So all the relevant terms, in particular, this one is not going to be important as the leading post-Minkowskian or post-Newtonian order, but it will be at the next one, which is what we were talking about. So how do I determine that? Well, that's a very long story, which I don't have time for. But right. Small technical difficulty. Okay. I'll say this in 5 minutes.
I don't think you should worry about that.
Okay. I will try that. So I was describing, how you would look at this from a purely classical, effective world line action point of view. Okay, so let's switch gears. Think about how would amplitudes people think about this. And so an important and to me still amazing development that came from scattering amplitudes is that to get to including any order and spin, to get to this next to leading order, well, first to get to the leading order level, to any order and spin, you only need to consider this single, looks like a Feynman diagram, but actually it's not a Feynman diagram, it's a so-called unitarity cut. Or more accurate. Let me try that again. It's like a Feynman diagram, but better. Why? One reason, because it's gauge invariant. There's not much difference at this so-called tree level or 1 p.m., but at the next order, it turns out you only need one more of these unitarity cuts, which is this one picture here with one loop, and one loop corresponds to the next to leading order, or g squared, second most Minkowskian. And the thing about unitarity cuts is that, again, they're gauge invariant and they're built out of, so each of these blobs is itself a gauge invariant amplitude. And we can see it's built out of these 3 pieces. 2 copies of this so-called 3-point amplitude in red and blue, and then 1 copy of this purple guy, which is the so-called Compton amplitude, because it looks just like amplitude for Compton scattering. If those were the solid lines were electrons and the squiggly ones were photons, that would be a Compton amplitude. Now they're black holes and gravitons. But so the point is, working in the scattering amplitudes framework, everything you need to know at the second post-Minkowski order is going to come from knowing about these simple building blocks, this 3-point amplitude and this Compton amplitude. And so it has been understood in recent years that that 3-point amplitude, if you want to include all orders in spin, so all of the multiple moments for a black hole, all you have to do is take the relevant amplitude without spin and multiply it by this factor of e to this spin vector. So this is that rescaled spin ring radius vector A dotted into the momentum of the graviton.
That's any order.
In spin. Yes.
Fixed G order, any order is
Fixed, it's definitely linear in G. So each of these, so this 3-point amplitude building blocks, they're all tree level or linear in G. But we can see a correspondence between that and the linearized Kerr solution. So linearized in GM, but all orders in A. And it's just this exponential. And some of you may have heard of the so-called Newman-Janus trick, or that, I think that's usually the name, but it's like taking position and sending position to position plus IA turns Schwarzschild into Kerr. In some sense that I'm not going to get into, but that's the so-called Newman-Janus trick. If you've seen that, this should look a lot like that, because that graviton momentum, it's a wave vector, it's really like a derivative. It's Fourier conjugate. So e to the I derivative dot some displacement is displacing you by I, the I coming from the Fourier transform. So in a sense, that's the same thing as the Newman geometry.
It's just special alternative, like, or when we think of field theories with particles.
So like black hole solutions and alternatives, yeah.
I'm thinking now, the scattering of particles that have input that speeds with field theory. But you can, like, this kind of turn the switch on and the low speed.
Well, in a sense, I mean, to linear order and spin, like actually, it's universal. There's no, so I was talking about like quadratic order and spin, we have this adjustable coefficient, but at linear order and spin, everything looks like a black hole. Just like at zero order and multiple expansion, everything looks like a point. So in that sense, at least linear order and spin, it's still valid. Well, actually, that statement I just made might be special to GR. I'm not sure. Yeah.
So I'm a little confused by the yellow underlined terms. So are these the ones you recover from this?
No, you
So
only,
it's just these two under 2 p.m. that you're getting the. So, are these all orders and spin terms on this table somewhere? Because you're saying it's only up to linear order G, so you can't go too far to the right, right?
well, so that's the funny thing about, oh, that's the other presentation. But, you know, assuming this is small, but working to orders in this is what we're doing. So I claim a linear order in this guy, all orders in this guy, so that's the bottom diagonal. That's the
Okay, so it is this entire yellow.
Yeah,
diagram.
it's the entire yellow,
That's what I wanted.
all the way down to infinity.
Got it.
So-called tree level or 1 p.m. and you all get it, you get it all from that simple diagram on top, pointed to by the yellow arrow. And the next to bottom diagonal, the orange, in principle, to all orders and spin, you get from this guy. The thing is, these pieces, these 3-point amplitudes, we do know to all orders and spin. But that constant amplitude, we don't. In fact, well, I wrote something there, but we know that's false. And
it's G squared.
this is G squared, exactly. So this triangle, one loop thing gives you the G squared, which is the next to bottom diagonal underlined in orange. It is more than that. That I is doing something funny. That I is not in a, yeah, it's a whole very fun story, but it looks remarkably simple. And I mean, I should be pointing out, this is true for helicity states. So like the graviton has a certain helicity. Say if it's plus or minus, that sign changes to plus or minus for the two different helicities of the graviton. It just turns out that in this triangle cut, it gives you the one loop amplitude. Only a certain helicity, well, let's just say you can get the entire answer from a certain helicity configuration, which is the one shown. Sorry. Yeah. How do I find what is this Compton amplitude? Or how do you find these actually give you the whole. Yeah, like just talking about this 3-point amplitude tree level thing. Okay, good question. And one more. Good. All right, so here's what we were just saying, that 3-point amplitude and claiming that it has this form. How do I get that? So I was saying there's a correspondence with the so-called linearized curve solution, which again is taking the exact curve solution, linearizing it into GM, but keeping all orders in A. So I claim that when you do that, you get this metric perturbation, thinking of this as a metric perturbation on flat spacetime. where, so here, there's no I, there's a star. That I kind of became a star. And what I mean by a star derivative, nu is absolutely sigma a rho derivative sigma. So that's some matrix, which I'm taking the exponential of that matrix here. Okay, but I'm just claiming this is a way to write the result of taking the Kerr solution and linearizing GM.
You can use the laser point.
Thanks. So how do we, translate this into this? Well, I hope they already look quite similar. And this K is essentially I derivative. But yeah, more or less, there is a direct correspondence between this 3-point amplitude and the linearized solution of the static object here. I just wrote proportional to here. It's whatever it is for the non-spinning thing times this factor. And essentially, the amplitude is this solution contracted into graviton polarization. I can give you several references that go through this. But yes, very good question. And let me try to. Okay, so that's the 3-point amplitude that we need. How about that Compton amplitude? So there's a very interesting story that started with a paper by Arkani Ahmed, Fong and Wong from 2017, where the word black hole does not appear in the paper anywhere. The title of the paper is Scattering Amplitudes for All Masses and Spins. In that paper, they were just considering, if I consider, so now quantum, thinking about quantum particles of arbitrary spins and masses, what is, like, one question, what is the most general amplitude, scattering amplitude that I can write down? In fact, they were very specifically looking at these kind of 3-point amplitudes for massive higher spin particles meeting photons or gluons or gravitons. They were also specifically looking at these 4-point Compton type amplitudes. And they, again, let's just say they were considering the most general such amplitudes, but they also said, look, there are these really special ones, which they called minimal coupling, which you should be very careful that this word gets used in many different ways and it's not always the same, but they use that word for a certain class of amplitudes. But let's just say they were, in a sense, the simplest ones, and I think maybe the most specific way in which they were is that they had the best possible behavior in the high energy limit. So essentially where these massive guys go towards being masses, or where their masses become negligible. It was later understood by people like our speaker for tomorrow, who won't be here, Alfredo Guevara, and also in with Alfredo and myself and Alex Otero, that those amplitudes correspond to black holes. And at least for the case of the 3-point amplitude, there is this exact correspondence, and that, which can be related to linearized Kerr in the way that I was telling you about. In the same paper by Arkani and Wong, they wrote down a Compton amplitude after some processing, the one you're looking at on the screen. But they knew it was not, so it was consistent with the 3-point amplitudes, consistent with unitarity, factorization, and those 3-point amplitudes, but They knew it had problems. And so I'm skipping a lot of things here. But, they weren't thinking about classical spin. They were thinking about like spin half, spin 1, spin 3/2, spin 2. And they knew their amplitude had problems after spin 2. When you translate that into classical spin, it corresponds to that amplitude having problems at 5th order in spin. And specifically, it has a spurious pole, which you can see here. So this quantity is 2 spinners, square roots of the graviton momenta. That factor appears to the 4th power out front and in the denominator in the exponent. So if I think about expanding this in powers of the exponent, right, at the 5th order, I will get that spurious pole factor in the denominator. So, and more or less, they didn't say this, but it was later said that Compton amplitude comes from those 3-point amplitudes via BCFW recursion, dropping the possibility of a contribution from infinity. Sorry, it might be Greek to all of you. But so it still is a question like how to fix it. In fact, it's already a question, is it even right up to 4th order in spin? Right? It has no spurious pole, it has no obvious problems at 4th order in spin, but does it actually correspond to Kerr? So that was, again, it's not going to be simple to match. You can't get this from matching linearized Kerr. You might think, okay, what if I expand Kerr to G squared? Is that going to be enough? Actually, no. In order to fix this, you have to think about perturbations in Kerr. And in this work with my collaborators, Fabio Bautista, Alfredo Guevara, again, and Chris Kavanaugh, who is a self-forced expert, an expert at doing black hole perturbation theory, we looked at a correspondence between that Compton amplitude and the classical process of scattering gravitational waves off of a Kerr black hole. So using black hole perturbation theory, the Tucholsky equation for gravitational perturbations of a Kerr black hole. And long story short, we did confirm that you get the same answer through 4th order in spin. While at 5th order in spin, where there's the big question of like, how is it to be fixed? We got an answer, but we're not sure about it because there's a lot of trickery involved. For example, including this analytic continuation from the actual black hole case, which is where we can actually solve this Tucholsky equation with boundary conditions of the horizon, to this naked singularity case. We could only get reasonable results by first solving the problem with the black hole, analytically continuing to this machine. Okay. In any case, I would say it's still an ongoing problem and a fun contact point between amplitudes and classical gravity. Like now we're going, so amplitudes has taught a lot to classical gravity, especially about how to compute higher orders, how to do integrals, which I haven't talked about at all, but I bet Mal talked a bit about it. And I particularly like this example of now classical gravity is giving input back to amplitudes, or at least trying. Well, there's definite input up to this 4th order in spin. Like we unambiguously confirmed that that Compton amplitude is right up to 4th order in spin. Stay tuned for more developments about the higher orders if you're interested. I think I'll leave it there. Thanks very much.
Anyway, people are busy, can just leave and we discuss. But I mean, the scattering of the gravity of Kerr black hole should be known for all the spin, for all powers of spin, not just at a page.
Okay.
Let's say what the scattering is. Say Compton,
Like that
what
one.
is that?
Yeah. Well, it's supposed to represent graviton, like squiggly lines are gravitons and the solid lines are black holes. or effective black holes, at least.
And P is just one of those things.
Okay, so P is the momentum of the incoming black hole. K2 and K3 are the momenta of the gravitons.
So they were there. So P is the income, and then P minus K2.
Exactly, yeah. So the last leg you can get from momentum conservation.
Plus, it's conversely. It's not even real. What you're
No, it's not real. And I should have, so this is in helicity states. So these good, I should have put a plus on one of these K's and a minus on it. Okay. So yeah, it's complex. And just what are these weird so like a graviton momentum or any massless null vector can be written as the how can I say this? Well, let me just say, yeah, it's a product of two spinors. This is the so-called spinor helicity notation. I think the simplest way of write that is a null vector or a massless momentum is written as a product of two spinors. That's what those square brackets signify. Was there a question?
I would thought, the scattering of gravitational care.
Yeah.
That is known, no? Since many years. Isn't it?
Yeah, I think you're thinking of the absorption cross section.
No scattering, just absorption.
Yeah, I mean, so this thing will include that, but also all of the conservative effects as well.
So and the computational element doesn't include the Erasmus scattering?
Our computation?
No, the page computation doesn't. Okay, I might remember.
I mean, I think it could in principle. But so also the thing about Page's stuff is he was sending in a wave of a given like L and M,
Yeah.
like spherical harmonic decomposition or spheroidal. We want plane waves. We want to send in a plane.
Mhm.
I know it sounds like it sounds trivial, but it's highly non-trivial to decompose these plane waves into spheroidal harmonics and curve, etc., and get the amplitude expressed in this kind of form. And I have a slide that will answer your questions in the other guy. Or like, what's the problem with orders and spin? Okay, so again, here's like schematically a picture of this scattering, and you get an amplitude of the outgoing wave. So classically, again, this has nothing to do with quantum field physics. This is classical gravitational plane wave comes in, spherical waves come out. What's the amplitude as a function of the direction it's going in, basically? So here I'm writing down schematically the answer, exact answer from the Minkowski equation. The only thing I've omitted are coefficients which depend on the angles. There's 3 angles in the problem. So there's an angle. Let's say there's the incoming momentum doesn't have to be aligned with the spin, and then there's the outgoing momentum. That ends up with 3 angles. So there are coefficients here which depend on those 3 angles. Otherwise, this is the dependence on the physical. So G in omega is the frequency of the incoming wave. That's our small parameter. But also there's a dependence on the spin. Okay, and you can see this pattern for the first 5 lines. It turns out to be polynomial in the spin. And so that upper diagonal is exactly what we wanted. The tree level, so linear in G, that Compton amplitude at tree level or at linear order in G, that's exactly that top diagonal. And we had no trouble extracting it, and it perfectly matched that weird exponential. Okay, but then it's no longer polynomial in the spin at the next order, the one where we wanted to pick off that a to the 5th term. It's got these weird, so psi is the digamma function. And then you got this line. You can see these things also have branch cuts precisely at the boundary between a black hole and the naked singularity. And as I think I mentioned, the problem we actually solved, the only problem we actually know how to solve at the moment is let there be actually a black hole. So A is less than GM. There's a horizon, you put a boundary condition at the horizon. Crucially, that there are only ingoing waves, no outgoing waves. That's the problem we solved. But then in order to make it look like the other lines, or in order for there to be this last term with A to the fifth and linear in G, the only way to get that kind of thing from this is go to this limit, expand here, after analytically continuing past that branch cut between the black hole and the naked singularity. So we did that, and we got some answer, but we're not sure of it because of everything I just said. Yes.
Because like this is the complication. Or the gauge is gauge. So particular.
I think this is gauge invariant. Definitely gauge invariant.
Okay, but you fix the terminal polarization. I mean, the special rule for the quantum
Yes,
is very much in that
that's right.
particular
Yeah, particular helicity state.
exact.
Yes.
Yeah. I'm just trying to see what else to change that.
Yes, so, okay, the two. So you could have plus minus, you could have minus plus.
Yeah.
Those are the same modulo complex conjugation.
Okay.
So it basically comes down to there's the opposite helicity or the same helicity, which is also related to minus minus. So yes, this one is very boring. The answer that is predicted from BCFW, for example, from 2-point amplitude is K2 plus minus K2 minus K3 dot A. That's the answer that comes from BCFW. Tucholsky confirms this, at least through 6th order and spin. We only went to 6th order and spin in our paper.
Yes, my question was more like, you know, the arguments like that we show in this notation, like, is that gauging what advantage from that representation?
Yes, yes, because
Maybe that was not completely clear.
because that's not the best place. Well, in any case, yeah, here in the exponent, right, you have upstairs and downstairs. So the helicity, wait, and same for. So that exponent is gauge invariant. There's the factor out front, which is not, but the amplitude, again, these are in certain helicity states, so they should have a certain scaling. But yeah, so it is gauge invariant. Yeah, please.
Sorry, I'm fishing for things that I know. So as you take A going to N, so if we're thinking of the curve solution, we know it's the middle. Like our time is the middle. Does that phenomenon exist in any way?
Not in an obvious way, but yes, we should certainly be worried about things like that. Or even if this whole program makes sense, like so I said, what we actually did was solve it with the horizon, get the answer, and analytically continue.
Right.
What if we first start with a naked singularity and then try to solve the Tucholsky equation? Like, does that even make sense?
Yeah,
Because
that I don't know, but I mean, the R-time instability exists in the case where I still have a black hole. I'm just bringing A close and
right. Can you remind me what exactly is Aristotle's instability?
you have divergence in curvature and particular projections of the curvature across the horizon. That might be irrelevant here. Your gathering might be just something that is very local to the horizon and then it's not seen to a certain level of far surface.
It might be very relevant. So, and that's different from the blue shift instability.
Yeah, so we have an interior
At the inner horizon. This is at the outer horizon.
Yeah.
it could be very relevant. I don't have the answer.
Yeah, and also related to some work that Aaron and Sonia and others did some years ago. Potential turbulence and particular instabilities that may arise in second order. So I still wonder what the manifestation of that is.
Good question.
So if I shift sigma by P. Is that right? Sigma by U?
Like gauge invariance that he was asking about?
No, that's the difference.
Okay.
I think you call it shifts.
Oh, I didn't even mention that, but it was on the slide. Yes. And the other presentation. Yeah, okay. This needs some explanation. So separate work by these two groups, Baran et al. And Ahuja et al. We're trying to, I'm saying boots, well, like they were trying to figure out how to fix that Compton amplitude. And one thing that they noticed, and so trying to do it with no input from like actual black hole physics. Okay. One thing they noticed was that that amplitude has this property. Actually, the way it was phrased in both of their papers originally was it's a property of that of the triangle. Or if by Q I mean K, the momentum transfer in that triangle diagram. They noticed that for the black hole case, unlike a generic case, say with neutron stars, like for example, where this coefficient is not 1, etc. That symmetry is broken, but it holds for black holes up to spin to the 4th. And at that time, they were just assuming that that was right, at spin to the 4th. Okay, so they conjecture. All right.
The symmetry is not a conjecture. The symmetry is a definition of spin. Find spin about this.
No,
In the spin vector, as your S mu equals something involving the
but that was the momentum of the massive guy. So S mu nu is epsilon mu nu rho sigma, and essentially the momentum of the massive guy whose spin this is. And then my spin vector.
and sigma is the same as A.
Sigma is the same as A. It is indeed.
It's a symmetry. You should sigma by
No.
P.
So it's P is not Q.
Yeah,
So this
I don't care, but there's a P, there should be asymmetry. I don't know if Q or Q is there.
So Q is the sum of the graviton moment. Okay. And so if I do that shift here, it changes.
So this P in the formula is the P of the black hole. Of the
That's
gravity.
right. Of the black hole.
So to shift sigma by P, the formula is better stays the same. Because we need definition very constant.
If I shift A,
So A is sigma, this one's because it is.
sorry, yes, they are the same, indeed.
Okay, so if you shift A by P, the formula is better being variant. This is there.
Absolutely. If you shift A by P, nothing changes. Here. Yeah,
You shift A by P.
no, okay. So if you,
the symmetry is constant, will that be true?
Yeah, so the formula is better being variant.
well, yeah, well, this, I mean, the spin tensor is invariant under that shift. Okay, but other things are not. In fact, yeah, obviously. Yeah, quite obviously, this is not invariant under A goes to A plus P. Nothing.
So S mu is not a fundamental variable.
No.
So A has 4 degrees of freedom, or 4 degrees of freedom.
So A is constrained to be orthogonal to B, actually. Okay.
Oh. So A dot P equals 0, is that?
Yes, A dot P equals 0.
Okay. Okay. That helps.
Okay. But in that formula, if you shift A by K2 plus K3, K2 minus K3 is what is meant by Q there,
Then it's okay.
then it's invariant, non-trivially, but it works out. So they noticed this, they said, that's nice. What if that holds to all orders? And that is highly constraining in the space of possible things that this amplitude could be. And in fact, if you assume that, and if you assume a best behaved high energy limit, together they fix a unique answer at spin to the 5th. And that answer does not at all agree with what we got here, but again, with all of our caveats. So I would say the jury is still very much out on this question.
They agree with nothing else.
Oh yeah, they completely agree with each other. And they basically actually did exactly the same thing, which is, they phrased it differently, but they did exactly the same. Notice this pattern, assume it, but conjecture it continues.
This is moved for Travis presenting stuff on the appearance of the new non-Wilsonian operator.
Yes and no.
Okay, yes,
That problem of there being extra Wilson coefficients came up in that paper where they made this spin shift symmetry and conjecture for what spin of this should be. Yeah. That's the paper where that problem of too many Wilson coefficients in the field theory compared to Whirlwind theory came up. However, for black holes, that's not that big of a deal. That's more of a question for like a general body exclusions.
but it also appears simplified.
No, actually, so the extra Wilson coefficients show up at spin cubed. Spin cubed, that's spin cubed.
More questions? You are here next week.
I'm here next week and Monday through most of Wednesday of the final week.
So now.
Yeah.
So let's, thank you.
No, there won't be any special deal. I sent, as usual, some suggestion in the WhatsApp groups. If you're not in the WhatsApp, okay, you can be part of it, just send me your number via email.